Good afternoon, everyone. So I'm Henry, founder and CEO of Microtower, where we print nature's surfaces to solve human problems. We're a Sydney-based advanced manufacturing company, and today I'll be talking about recent advancements in our Sharkskin films for drag reduction and their application to aviation for improved efficiency and capability. So over millions of years, nature has developed these microscopic patterns that provide functional solutions. You might be familiar with some of these things, but things like adhesive gecko feet, anti-reflective moth eyes, self-cleaning lotus leaves, pitcher plants that have antibacterial rims, mammoth beetles that can actually harvest water from the desert air, or sharks that swim efficiently through the water. These are all properties that arise due to microscopic patterns on the surface of the plant or animal. And Microtower, our company, has developed an advanced manufacturing technology, what we call nature's 3D printer, to print those patterns and recreate those valuable properties. So aviation has a burning fuel problem. Every year, commercial aviation is spending almost $200 billion on fuel, producing almost 1 billion tons of carbon, all while operating on razor-thin margins of 2 or 3%, if not negative. This is being spent on overcoming drag, so burning fuel to push your plane through the air. And in spite of this cost and the climate challenges that we are facing, the aviation sector has trillions of dollars in fuel-burning assets, meaning that we aren't going to be able to transition to renewable power sources for decades to come. So nature has a solution for this problem, and we copied it. If you take the Mako shark, which is the fastest shark in the world, and look at it under a microscope, you'll find thousands of these microscopic grooves called riblets. If you've ever had the fortune or misfortune of touching a shark, you know it feels like sandpaper. That's because of these microscopic structures. And these riblets reduce friction drag by up to 12% in air and water. So the Mako shark evolved them to become a more efficient hunter. And we print riblet film product that our customers apply to aircraft to reduce drag, save fuel, improve capability, and decrease emissions. So riblets reduce drag by organizing turbulent flow near the aircraft surface. And if we consider just commercial aviation, our riblets could save up to $20 billion in fuel and 92 million tons of carbon annually. For example, if we applied this to the RAAF's fleet of airlifters, fuel savings would be in the order of tens of millions of dollars every year. These drag reduction savings also provide enhanced mission capabilities, including increased range, payload, and endurance. And so for defense, this means customers can reach and sustain missions farther afield using the existing fleet, so the same platforms. So to copy Shark's riblets, we've invented nature's 3D printer, or what we call direct contactless microfabrication, which is our proprietary advanced manufacturing technology. With this, we can print not only riblets, but any number of these surfaces from nature. And there are 3 steps in the process. So we start with the untreated surface and adhesive-backed film. Although we can apply this to any number of materials, we print it on metals and composites, and apply a UV curable coating. So this is just a paint that cures instantly when you hit it with ultraviolet light. These materials are used in a wide number of industries, including aviation, typically just to improve throughput, or another way to say it is so you don't have to watch paint dry. We then expose it, so that will remain uncured until we expose it, and we expose it with micro-pattern light that matches the desired riblet pattern, traversing across the surface and only curing where the light hits it. It actually grows the riblets within the coating, which gives us the ability to control their topology. You then remove that uncured coating, what we call developing, to reveal the riblets printed directly onto the surface. So what makes DCM different is that we grow these riblet structures with light, which gives us 3 key competitive advantages. We can provide double the savings, so we can print high aspect ratios and complex riblet designs that can save up to double the fuel of alternative technologies. We have the unique advantage of rapid iteration. So we're the only technology that can rapidly iterate for different customer applications, new properties, and optimizing for better performance. We can already do this an order of magnitude cheaper than alternative technologies. And because we print with light, this will trend to 0 with time, as we just need to change that light field in order to change designs. And then we do all this with the scalable manufacturing process. So a single DCM printer can produce up to 100 square meters of riblet film per minute, meaning that we can scale and deliver to more customers with low marginal costs. We've had significant traction to date with our aviation product. We've already demonstrated 7% friction drag savings in multiple tests with Lockheed Martin. We've delivered on 5 contracts with the US Air Force, as mentioned in the introduction, to develop riblets for their legacy transport aircraft. We produced dozens of riblet designs and delivered orders to some of the largest OEMs, original equipment manufacturers, MROs, maintenance, repair and overhaul providers, and operators, both in defense and commercial aviation. Our technology has patents granted in a number of jurisdictions, and we've built our pilot manufacturing facility in Sydney, where we're printing square meters of riblet product today. So recently, we produced riblet designs that approach the ideal aerodynamic geometry. These are high aspect ratio designs called blade designs, which are known to be the best in terms of drag reduction. And we're the first to manufacture these at the microscopic scale needed for aviation applications, due to our ability to print with light and not touch the surface. Another key requirement for our product is obviously durability. So we need to be able to survive the extreme conditions aircraft experience, including ultraviolet radiation, ice and dust abrasion, temperature gradients, and fluid exposure. So we are integrating into existing program depot maintenance cycles, so our target lifespan is on the order of 5 to 10 years. This is a non-trivial problem, but we've made significant progress. We're using an aerospace-based UV curable material already, so it has the same bulk material properties, and we've improved on the mechanical durability with new formulations that perform up to 20 times better than those in the past. Again, standardized sand abrasion testing, and they've even survived being driven over by a car and hit by a hammer, which is less scientific but more entertaining. We also plan to meet relevant Boeing material specifications by the end of this year, which means that our material will be qualified for Boeing transport aircraft. Late last year, we completed our first manned flight test in collaboration with Matt Hall, who's the Red Bull Air Race World Champion, who's the owner and operator of the Zivco Edge 540. This was chosen due to its size, wide range of performance capabilities, onboard data acquisition systems, and of course the flight test capabilities of Matt Hall. We manufactured and applied 10 square meters of product for the flight test program, and a speed increase of 1% was anticipated, correlating to roughly a 2% net efficiency gain. It was applied by removing the adhesive backing and then applying with a wet solution, similar to how car and aircraft decals are applied, but we'll be moving to a dry application method in the future in order to minimize the time and cost of application. 4 different riblet configurations were tested, covering the top and some different portions of the bottom of the wings. And with just that application to the wings, we did achieve that 1% speed benefit across all the riblet configurations versus without riblets, equivalent to a 2% net efficiency gain throughout the flight profile. We expect this to be equivalent to a 4% net efficiency gain for full aircraft application at scale. What that means would be a net 4% fuel saving. So to give an example, if we look at the RAAF's 8 C-17As over a 5-year time span, that is the wrong slide, so I'll do this one. So if we take, for example, the C-17A fleet over a 5-year time span, this would save on the order of $30 million. And we actually have a proposal under assessment at the moment under the Defence Innovation Hub with a key OEM partner to deliver this to the C-17 fleet. So critically addressing durability and material qualification, application, repair and maintenance to make sure we meet the customer needs, add no additional downtime to the scheduled maintenance and no other maintenance requirements, as well as performance optimization and return on investment analysis over the product lifetime, taking into account drag reduction, flight testing, and also CFD analysis. What's next for us? So in 2023, we'll have our first wide-body aircraft riblet product ready for certification and rollout, which means our product will meet the OEM specs, so for example, the Boeing material specifications. Again, we'll reach that by the end of this year. We'll be scaling up our manufacturing capacity to be able to cover large transport aircraft, so hundreds of square meters of product. We'll demonstrate the product life cycle to meet customer needs. So I mentioned application, repair and maintenance and removal, integrating into scheduled maintenance, and critically not adding any additional downtime. We'll conduct further flight testing to quantify and validate that drag reduction performance and long-term in-field durability, as well as launching our product on smaller, unregulated aircraft who can benefit from the savings in the near term prior to large transport aircraft certification. And finally, we'll actually be doing some further testing of new riblet designs, more interesting, complex 3D ones, that can increase our savings up to 12%, and we'll be doing third-party testing with a defense prime on that front. What we're looking for to engage with today, so we're looking for launch customers, for smaller platforms who can benefit from that 4% improvement I mentioned in terms of either fuel economy or range, endurance, and payload in the near term. We'd love to engage with defense customers to make sure we understand their needs and requirements and meet them. And also scale partners, so operators of the large transport aircraft we're targeting for scale flight testing and certification. So if you have a platform that could benefit from improved fuel efficiency, payload, endurance, or range, please come speak to myself or my colleague Duncan. and our details are there.
Yeah, my understanding is, my understanding is that parasitic drag is also reduced by doing aircraft washes as well. So do you anticipate that this sort of regime will continue with this new bill that's applied?
So, sorry, you said with regard to washing the aircraft, you said?
Yeah, just
yep.
Aircraft washes are used.
Yes.
Just to reduce parasitic drag, which is what this is what it's doing.
Yeah.
So do you anticipate that those washes can be, reduced or eliminated, right, from the maintenance regime if you apply this bill?
So our target is to have the same maintenance procedure, so the same cleaning process and washing processes is currently used on the aircraft. We aren't counting on it yet, but the material that we produce with these microstructures, as well as being a low surface energy material, have additional effects of being increasing hydrophobicity, which means organic material and matter can less easily attach and more easily wash off, so it may reduce the maintenance requirements. But our target for now is just to match, so we're not changing any of the existing maintenance. But this would be reducing drag as compared to a completely clean aircraft, so a hydrodynamically smooth aircraft.
So we have a quick question online, which is why and how this geometry helps. Can you please explain the physics?
Sure. So essentially, what occurs? So this works in turbulent flow. Once you have fully transitioned turbulent flow, there are characteristic vortices known as hairpin vortices. So on the scale of a hair. That's why these things are on the scale of a hair. A little vortex that forms, and it's quite predictable in terms of its diameter, depending on your flow conditions. It's related to wall shear, which is the tau in micro tau. What happens is by having these structures slightly narrower than the diameter of those vortices, it excludes them from the surface. So a lot of that scrubbing is only happening on the very fine tips of the riblet structures. So even though you're increasing the surface area, which is counterintuitive, you typically want to have as clean and smooth a surface as possible, you do get a net drag reduction effect. But we didn't work that out, the Sharks worked that out, and we copied it.
Thanks. And we have one last question online, which is, are there maritime applications? Can you coat a hull with it?
So definitely, sharks are famously originally from the water. We've been working for most of our existence in aviation. As I mentioned, we got our start with the US Air Force Research Laboratory. The critical missing piece there was ensuring that the material won't foul, so biofouling in a marine context is obviously a big concern. We actually have developed a new material that we manufacture out of that we tested in Sydney Harbour last year and didn't foul over 2 months. We have another set of materials that have just been checked after 7 months and are still not fouling. So it's earlier stage for us, but with those initial results, that's enough for us to give the confidence to go and put this on marine platforms. It is a different material, but the same kinds of structures. And because we're reducing friction drag, a lot of marine applications have a greater proportion of their drag being friction drag, so the savings can in fact be quite a lot larger.
Great, thank you. Let's thank our speaker again.
Oh. There's one. Yeah.
One quick last one. How about supersonic flying objects? Because the physics normally change a little bit for the supersonic.
So we haven't flown supersonic, but there has been previous work done in the supersonic regime, including on a supersonic aircraft. I think it was done in the 90s. If you get our details, I can send through that paper. But they do operate in the same way. It's a matter of scaling the riblet structures. They essentially become smaller, but they do still work in the same way.